Imagine standing at the edge of a vast agricultural region, looking out over thousands of individual farm fields. Each field represents livelihoods, food security, and land management decisions. Now imagine being asked to map all of those fields automatically using satellite imagery, accurately, consistently, and across large areas. This is one of the central challenges in modern geospatial analysis. While satellite data is abundant, high-quality labeled training data is not. Field boundaries must often be digitized manually, which is slow, expensive, and difficult to scale. So how do we build deep learning models that work well when we don't have enough thousands of labeled examples? This is where transfer learning becomes essential. Deep learning models are powerful because they can learn complex patterns directly from data. But that power usually comes at a cost: large training datasets and long training times. In Earth's observation, collecting labeled data can be especially challenging. Cloud cover, seasonal variation, and regional diversity all add to this complexity. Transfer learning offers a practical solution by allowing models to reuse prior knowledge. Instead of starting from a blank slate, we begin with a model that already understands how images work. This approach is particularly valuable in geospatial applications where visual patterns such as texture, edges, and spatial relationships are often shared across regions and applications. At its core, transfer learning is about reusing what a model has already learned. When a deep neural network is trained on a large dataset, it does not simply memorize images. Instead, it learns a hierarchy of features. Early layers learn basic visual patterns like edges and corners. Middle layers learn textures and shapes. Deeper layers learn task-specific representations. Transfer learning takes advantage of this structure. Rather than retraining all layers from scratch, we keep the parts of the model that already understand visual patterns and adapt only the parts that need to specialize for a new task. This dramatically reduces the amount of data required while still achieving strong performance. In practice, transfer learning usually follows a clear workflow. First, we select a pre-trained model, often trained on millions of images. This model serves as a starting point. Next, we modify the network architecture to match our new task. For example, we may replace the final classification layer or add segmentation layers for pixel-level prediction. Then we choose how much of the model to retrain. Feature extraction by freezing layers preserves learned features and speeds up training. Fine-tuning layers, on the other hand, allows the model to adapt more deeply to new data. This flexibility is one of transfer learning's greatest strengths. It allows us to balance speed, accuracy, and computational cost. Training deep learning models from scratch with limited data often leads to overfitting, poor generalization, or unstable results. Transfer learning helps overcome these challenges by providing strong initial weights, reducing training time, and improving model robustness. In many cases, models trained with transfer learning reach high accuracy faster and more reliably than models trained from random initialization. This makes transfer learning especially suitable for applied geospatial projects where time and data are limited. Transfer learning is widely used across Earth observation disciplines. It supports land cover and land use mapping, flood extent and disaster response, urban growth and infrastructure extraction, and crop type and vegetation analysis, among others. In each case, the same principle applies. Models trained on large, diverse datasets can be adapted to local or specialized tasks with minimal additional data. Now let's bring this concept closer to our module. Our focus is agricultural field delineation, a task that requires identifying precise field boundaries from satellite imagery. This problem is especially challenging in regions with smallholder farming systems, irregular field shapes, and seasonal landscape changes. One such region is Cambodia. Cambodia's agricultural landscape is dominated by small, fragmented fields. Boundaries are often subtle and difficult to distinguish visually. Traditional mapping approaches struggle to scale in this environment. Manual digitization is time-consuming, and training deep learning models from scratch would require large labeled datasets. By using transfer learning, we start with a model that already understands satellite imagery at a fundamental level. We then fine-tune it using a limited set of labeled field boundary specific to Cambodian agricultural patterns. Through transfer learning, the model learns to detect field edges and internal texture differences, separate adjacent agricultural parcels, adapt to local crop structures and landscape variation. Because the base model already recognizes the special patterns, the fine-tuning process becomes far more efficient. This allows us to produce accurate field delineation maps even with limited ground truth data. One of the greatest advantages of transfer learning is its scalability. Once a model has been fine-tuned for one region, it can often be adapted again for neighboring areas with only minimal additional training. This makes transfer learning a powerful tool for regional and national scale agricultural monitoring. Transfer learning changes how we think about deep learning in geospatial science. It allows us to move faster, work with less data, and still produce reliable, high-quality results. In this module, transfer learning enables accurate agricultural field delineation in Cambodia, turning limited data into actionable insight.